What is going on, guys? Welcome back. In this video, we'll be talking about limit laws. These limit laws are very powerful tools to have in our arsenal, and they're very powerful statements to make in calculus because they make the basis of everything. And the reason being is because we can now algebraically solve limits instead of having to draw functions out. And so, before we actually talk about that, I really wanted to talk about the limit once again, just reviewing real quick. Okay, so we said that the idea of a limit comes from us trying to get very close to this number c on the x-axis. So we get close or we approach. So we're getting close. All right, and sorry for my horrible spelling. Approach. Okay, so we could approach from the left. Sorry about that. We could approach from the left. And how does the y value behave? So on the y value, the function it looks like it's getting closer and closer and closer and closer to this point. And if we approach from the right, so from the left, now from the right, as we get closer and closer and closer and closer and closer, it looks like this value. And so we have two sides. This is the left hand limit. Left limit. And this is the right hand limit. All right, and you'll see notations. The limit in books, the limit as x approaches c with the minus sign is from the left of f of x is equal to the limit as x approaches c from the right of f of x. So if the limit from the left hand side is equal to the limit from the right hand side, well, our two-sided limit exists. The more common notation seen, the limit as x approaches c of f of x is equal to a value. So let's call this value L. L. Okay. And so this means the two-sided. Okay, with that being said, guys, all right, these limit laws can be applied. Limit laws can be applied to one-sided and two-sided. All right, they could be applied, but if we're given just the one-sided and two-sided limits, the better approach would be to graphically or use a chart to show it. But we could definitely use limit laws. Okay, so what are these limit laws? So first off, we have some conditions to make. So suppose f and g are functions, and suppose we have a constant c. Okay. So if we try to add two functions, and of course they are with respects to x, to the x-axis. Okay. Well, okay, now, what if we want to add or subtract the limits? So for the first and second one, if we have the limit as x approaches a of f of x plus g of x, so the limit inside of it, or f of x minus g of x, well, we could. So if we have one combined limit, we could split the limit apart. Okay, so we have the limit as x approaches a, and plus the limit as x approaches a of g of x, and we also have the limit as x approaches a of f of x minus limit of x of g of x. Okay, so pretty much we could split these apart at any time we want. Now, what if there's a constant inside of our limits? So say we have the limit as x approaches a of f of x. So something like 2x squared. Okay. Something like 2x squared, and this limit's here. Well, we could split it apart. We could take this limit outside. This 2 would go outside the limit. So it'd be 2 times the limit as x approaches a of our x squared function, if that makes sense. Okay. So we are allowed to pull out any constants. Okay. Now, what if we have multiplications? Similar to addition and subtraction, all right, we're allowed to break up functions if we'd like, instead of having to multiply them out. So the limit as x approaches as x approaches a of f of x. Oops, sorry about that, guys. You guys can't see that. Of f of x times g of x gives us this breaking apart limit where we're multiplying out the functions right here, guys. Sorry about that. Let me zoom in a bit more. Okay. We're allowed to split apart the functions right here. The limit as x approaches a of f of x times limit as x approaches a of g of x. Now, what if we wanted to divide them? Well, similar case. All right, so we could split them apart. So if we have a quotient inside of our limit function, or our limit operation, the limit as x approaches a of f of x over g of x, we could, in the numerator, write a limit out for f of x, and in the denominator, write a limit out for g of x. Same thing with powers. So if we are evaluating a limit raised of a function raised to a power, so limit as x approaches a of f of x of n, we could take that. We could say instead of doing that, we could take the power or the limit, the value of the limit of the function, and raise it to that power. So like if we had, once again using x squared, instead we could take the limit as x approaches a of x and then raise it to power 2. You guys can't see that. Sorry about that. Okay. Now, these are very powerful claims, 7, 8, 9, and 10. In fact, we'll prove it later on, but all right, so these are all functions. So the limit of a constant as we approach a number is a constant, so it is the constant. All right, if we're raising a function to a power, we're allowed to directly substitute our approaching value into the function. So, and same with a simple x or even a radical. And the reason why is because these are all functions. So 7 through 9 are functions. Or 7 through 10, sorry, are functions that are continuous in their domains. Okay? In fact, we'll be showing that too with this video, but pretty much as long as we're within a domain of our functions, we're allowed to directly substitute. So let's do an example. Okay. So we have, sorry about that, guys. We have the limit as x approaches 2 of 2x squared minus 3x plus 4. What does that equal? And we want to solve this using limit laws, because let's say we don't know that we could directly substitute yet. In fact, we don't know that yet. Eventually we could, once we prove it, but until then we can't really. And so, to do so, we use the first law, where we could split the whole functions apart. So, instead of taking the limit of the whole thing, we could just take the limit as x approaches 2 of 2x squared minus the limit as x approaches 2 of 3x plus the limit as x approaches 2 of 4. Okay? So now we have a constant. We could pull this out. We have the limit, and we can pull this constant out too. So we have the limit as x approaches 2. Oops, sorry guys, you guys can't see that. 2 times the limit as x approaches 2 of x squared minus 3 times the limit as x approaches 2 of x. And this is a constant, this is 4. Okay. So now, this is raised to a power. We can just directly substitute. So 2 times the limit as x approaches, so 2 times 2, or 2 squared, minus 3 times 3. Sorry about that, guys. And we're adding 4. Sorry for the shakiness. And so we're just simplifying this down. 2 squared is 4 times 2 is 8 minus 9 plus 4. So it'll be 12 plus 9 is equal to 3. Or 12 minus 9 is 3. Okay. So we can say this limit as we approach 2 is equal to 3. Okay. So I think that's going to do for today, guys. We'll continue this idea of limit laws in the next video. Later.